In today's class, we're gonna cover applications and processing of metal alloys. So when presented with a material selection problem, you guys should have some knowledge about the available materials. So therefore, we're gonna cover different type of metal alloys in this chapter, their properties, their limitations, how they are processed. So, when we are selecting materials, the most important thing is we look at the properties, and the properties will be changed based on what type of processing technique you are using, and it will depend on also the composition of the alloy, and it will also depend on if you have applied a heat treatment, because the heat treatment will change the microstructure, therefore the properties. So we all gonna see these, how fabrication techniques affect properties of materials, and how heat treatments will change the properties for alloys, metal alloys, and how we classify metal alloys. Metal alloys, they are classified into two classes. One is ferrous and the other is non-ferrous. And the ferrous alloys are those which has iron as the main component. These are divided also into two categories. There is steels and cast irons. So ferrous alloys, why they are very important engineering materials, and why? There are three reasons why ferrous alloys are very important. First of all, iron is abundant within the Earth's crust, and secondly, iron and steel alloys can be produced with economical manufacturing techniques, and ferrous alloys are very versatile, meaning their properties can easily be changed with different processing techniques, different heat treatments, different compositions. You can come up with a wide range of alloys, ferrous alloys, that will have a wide range of properties which might be suitable for your applications. So the bad thing about ferrous alloys are they are susceptible to corrosion. So the difference between steels and cast irons is in their carbon content. As you see, the pink region in the iron carbon phase diagram represents the steels, which steels have carbon content lower than 1.4%, whereas cast irons, they have higher amount of carbons, which shown with a gray region in the phase diagram, and it is between 3 to 4.5% carbon, and the microstructure of it is ferrite, graphite, and cementite. So cementite is actually what we call an unstable phase, meaning with a little bit of trigger, some energy, that will convert into a more stable phase, graphite. So under some conditions, some processing conditions, cementite will form graphite, which is more stable phase. Steels, besides having carbon, they will also have a variety of different alloying elements depending on what type of properties that you want to obtain from that alloy. So based on the amount of carbon and amount of alloying elements, steels are divided into two categories. One is low alloy, the other is high alloy, meaning one will have, the high alloy will have more of those alloying elements. So the low alloy steels, they are also classified into low carbon, medium carbon, and high carbon alloys. So as the name implies here, the amount of carbon content also changes. The lowest carbon content will belong to the low carbon, and high carbon will have the highest amount of carbon within those classification. Low carbon, medium carbon, and high carbon steels can also be divided into categories, different categories, and these will be plain. Plain means plain carbon steels, they only contain residual concentrations of impurities other than carbon. We see different names. We said plain is just mainly have carbon. There is HSLA, stands for high strength low alloy steel. These have better mechanical properties, greater corrosion resistance compared to just plain carbon steel. And there is again medium carbon, plain, and heat treatable. As you can see, what changes here, the addition of other alloying elements other than carbon compared to the plain ones. Okay, they can both come in plain, just the carbon is added, and also additional alloying elements can added to improve the properties. There are tool steels which are also have high carbon content. Besides that, they also belong to high alloy category because they also have a variety of alloying elements other than carbon. And you see stainless steel belongs to high alloy steels, meaning besides carbon it has other alloying elements such as chromium, nickel, molybdenum. These of course induce different type of properties to the material, such as very high corrosion resistance or high temperature resistance. Each of these alloys are named by numbers, as you can see here. These numbers will depend on they will represent the type of the alloy, and they will also represent how much carbon it has inside. For example, 1010 steel will have, it represents, it's a low carbon steel, plain low carbon steel, and it has 0.1% carbon in it. So based on that, different types of numbers are given to name the steels. There is also, we are seeing in this table, hardenability. This is not related to the hardness. It is actually the depth to which a material is hardened after putting it through a heat treatment process. It is not the hardness. Hardness is, remember, it's material's resistance to indentation. This is, hardenability is like the depth to which it can be hardened with a heat treatment. So as you can see, they are given pluses and zeros, so it tells you it gives you information about the hardenability of the materials, and seems like the tool steels are the best, as you can see, which you want them to be, because tool steels are used as drills, saws, and dies. You want the surface to be hard. So we are seeing the tensile strength, and we are also seeing ductility information here. And as you can see, in terms of ductility, stainless steels are the best, and in terms of strength, heat treatable steels and tool steels seems like the best options. And at the end of the table, we are also seeing the application areas for these different type of alloys. So we already covered those, right? and you can see a wide range of application areas for all those remaining different types of steel alloys. So the important thing here is the bottom of the chart. We are given the information that as we move from left to right, we are seeing the alloys with increasing strength, increasing cost, and decreasing ductility. So yes, stainless steels, they can be the strongest ones, or tool steels, they can be the strongest ones. But on the other hand, they will be costly, and increasing the strength also means decreasing the ductility. So this is of course a general trend, okay, general trend. We cannot comment on for specific different types of alloys because we have a wide range of different alloys, thousands of different alloys, ferrous alloys. So this is just a general trend we are giving. So as we increase the carbon content, you can also say that the strength is increasing, as we can see here, and it also decreases the ductility. So in this figure, it is given us how we can produce iron. So you will need 3 ingredients. These are iron ore from earth's crust, and coke. Coke is like a fuel. It generates the energy necessary for the reactions to take place. And there is limestone. Limestone is calcium carbonate, which is used basically to eliminate the impurities inside the iron ore. So this reaction, these ingredients are added to a blast furnace. Blast furnace is a furnace where very high temperatures are achieved for the chemical reactions to take place. As you can see, it is within a refractory vessel. Refractory means a vessel that can withstand very high temperatures. And we are seeing we added these ingredients inside, and the limestone reacts with impurities to form the slag. What we call slag is a layer that is floating on the molten metal that can be removed from the surface. And this way basically we are able to remove the impurities. So as you can see, some reactions take place within the blast furnace to generate iron. So the carbon reacts with the oxygen, produce carbon dioxide, and then carbon dioxide reacts with carbon to produce carbon monoxide. Carbon monoxide is reacting with iron oxide that is in the iron ore, and this reduces the iron oxide to iron, and also release carbon dioxide gases. And then for purification, meaning the removal of impurities such as silicon, alumina, these are reacting with calcium carbonate, and then they are removed from the structure, they are removed from the iron. Pretty much you are trying to purify, removing the impurities. And when they react with calcium carbonate, they form what we call the slag, as you can see, which is layers floating on top of the molten metal, which can be easily removed. After this process, the molten iron will be taken to other furnaces where it is gonna be enriched with different types of alloying elements, and different types of steels will be produced. So So we have said iron-based alloys, which are ferrous alloys. They are classified into two categories, steels and cast irons. The difference was the amount of carbon content. So we look at the nomenclature for steels. ASI means American Iron and Steel Institute. SAE means the Society of Automotive Engineers. So they generated this code for us to be able to classify different type of alloys. So as you can see, there is a 4-digit, and the first 2-digit is representing the type of the alloy we have. So depending on what type of alloy you have, it will have a certain number. So 10, 11, these represents plain carbon steels, and 15 steels that have high amount of manganese, and 40 and 44, these are different amounts of molybdenum, and 43 is where we have nickel, chromium, and molybdenum at certain compositions. So depending on what type of an alloy you have, it will have the first 2-digit will be different, and these can be found anywhere, like handbooks, internet, you can find. And the last 2-digit, where we are given XX, this will be the carbon content. So if it's 1060 steel, that means 10 represent it's a plain carbon steel. 60 will tell you it is 0.6% carbon. And stainless steels will have high chromium content. This is due to they have high corrosion resistance, and chromium provides the corrosion resistance. And as you can see, when we say stainless steel, they usually have chromium content bigger than 11%. So when it comes to cast irons, what is the difference of cast iron and steels? Usually you will see that they will tell you cast irons are ferrous alloys that has a carbon content higher than 2.1. This is more commonly 3 to 4.5. And these materials are easy to cast, and they have low melting point, and they are generally brittle. Since these materials are easily melted, they are suitable for casting. As I said before, cementite is actually a metastable compound, and under some circumstances it can decompose into alpha ferrite and graphite according to this reaction that you are seeing. So this tendency to form the graphite is usually regulated by the composition and rate of cooling, and it is also promoted by the presence of silicon other than carbon. If you add silicon up to 1%, it will also promote the formation of graphite. And again, also slower cooling rates during solidification favor graphite formation. So for most cast irons, the carbon will exist as graphite. So actually, so far we have seen only a little region of iron carbon phase diagram, but the true iron carbon phase diagram is given here, which has up to 100% carbon. We have only been seeing the small percentage of it. And you can see the graphite in the phase diagram. Alright, so what we're gonna do, we're gonna take a look at different types of cast iron, and I want you to get familiar with how the structure of different cast irons will look under microscope, because I can show you in these images in the exam, and I can ask you what type of iron is being represented by this a microscopic image. So the gray cast iron, it has between 2.5 to 4% carbon and between 1 to 3% silicon. And graphite in this case exists in the form of flakes, like cornflakes, and they are surrounded with a matrix that can be alpha ferrite or pearlite matrix. So an image, a microscopic image of a gray iron is shown in this pictures here. This one. Okay, so 11.3A. So that represents how gray iron looks like. Okay, you can see this type of structure because you see the graphite flakes, they have sharp and pointed tips. These creates regions for stress concentration when the tensile stress is applied. Therefore, this is actually weak and brittle in tension, but not in compression, because then under compression those points will not act as stress concentrators. And so the reason it was called gray iron, because when fractured, these flakes gives it a gray appearance. That's why the name came from. These materials are preferred when damping is required. Like they have excellent vibrational damping properties, and they have excellent wear resistance, high resistance to wear. Another type of cast iron is ductile, or also called nodular. So this is achieved by adding a small amount of magnesium or cerium to the gray iron before casting, and this produces a different microstructure, of course, therefore different types of mechanical properties. And graphite still exists, but this time it is in the form of sphere-like particles, as you can see in this image. The white matrix you are seeing on the microscope can be either pearlite or ferrite, depending on what type of heat treatment you are doing. Compared to gray iron, ductile iron is stronger and less ductile. Actually, wait, there is something wrong here. So compared to gray iron, this material is stronger and more ductile, but it is listed here as stronger and less ductile. They are trying to tell you there can be two types of matrix. One can be pearlite and other one is ferrite. And if it is pearlite, it will be stronger and less ductile compared to ferrite matrix. But in general, when you compare the overall structure with the gray iron, it should be more stronger and more ductile compared to the gray iron. Another type of cast iron is white iron. These materials have low silicon cast irons. These have low than 1% silicon, and they have rapid cooling rates. Therefore, the carbon will exist as cementite instead of graphite. And the fracture surface of this alloy has a white appearance. That's why the white iron term comes from. This structure, because it has cementite, it is brittle and very hard. This is virtually unmachinable alloy because it's being very brittle. Therefore, its application is limited to applications where you require a very hard and very resistant surface, but does not require a high degree of ductility. Malleable cast iron is the iron alloy. When we heat the white iron at temperatures between 800 to 900 degrees C for a long period of time in a neutral atmosphere, this will prevent oxidation. And this will cause the cementite to form graphite. It will now exist in clusters, as you see in this image. So this previous one was white iron. You can see the white regions within the cement, within the black cementite regions. And here the malleable iron is shown in this figure. And as you can see, we are seeing graphite in clusters, as you can see here, right? This structure, again obtained is a form of cast iron. It has high strength, relatively high strength, and appreciable ductility or malleability. So you are increasing the ductility of white iron with a heat treatment. You are obtaining a different microstructure, therefore different type of properties. And applications can include connecting rods, gears, pipe fittings, some other heavy duty services. A new type of cast iron is compacted graphite iron. Again, there is due to the presence of silicon in the structure. Carbon exists as graphite. And if you look at the microstructure, what is shown under microscope is it has worm-like graphite structure. It is like somewhere in between gray iron and ductile iron. However, now it doesn't have the sharp edges like the graphite flakes. Therefore, this will lead to a reduction in the fracture and fatigue resistance of the material. This type of structures, this type of microstructure results in high thermal conductivity compared to other cast irons, better resistance to thermal shock. Thermal shock meaning if there's a rapid temperature change, like quenching, for example, right? A fracture may result from it, but materials with high thermal shock can resist to fracture with these sudden temperature changes. And it has lower oxidation at elevated temperatures. Therefore, it will have important applications such as brake discs, flywheels, diesel engine blocks. Okay, so in summary, if you add magnesium and cerium, you will have ductile cast iron. Remember, if we go back here, if we add magnesium and cerium, we will end up with graphite as being spherical like particles. here we are seeing that the matrix can be pearlite or ferrite. So it depends on the degree of cooling. You see, if you do slow cooling, it will lead to ferrite, alpha ferrite. If you do moderate cooling, it will lead to pearlite. If we do without addition of these elements, if we do fast cooling, remember, without the presence of silicon, we do fast cooling, we obtain white iron, which is a cementite and pearlite. If we look at pearlite and cementite, and it looks like this. Let's take a look at the image here. So white regions are seen on the background, pearlite, and these regions are cementite. So if we do, however, the heat treatment as we talked about for malleable iron, if we go to temperatures around 800 to 900, they said it's 700, they hold it at that temperature for a long period of time. And when it is done, after you hold it, depending on how fast you cool it back to room temperature, it might have pearlitic malleable or ferritic malleable structure. So if we take a look at this, graphite exists as clusters as we see, but the background, the white region, can be ferrite, alpha ferrite, or pearlite, depending on what type of properties you want from that material. So we are seeing that you can actually see that a wide range of compositions and structures can be made possible with different types of cooling rates, with different types of compositions, and what is the initial structure you are starting from. So all these will give you different type of structures, therefore different type of properties. So it's very versatile. We are also seeing the gray cast iron. Again, if you do moderate cooling, it leads to pearlite and as a matrix. Slow cooling will lead to ferrite as a matrix. Both will show you this type of structure we have seen here, right? The gray iron, graphite flakes right there. Okay, so these are representing the gray cast iron. This was white cast iron. We make malleable cast irons here, and these represents the ductile cast iron with the addition of magnesium and cerium. So limitations of ferrous alloys, as we said, they have poor corrosion resistance. This is very important to have high corrosion resistance, because these type of corrosions that can happen during the usage of these materials can lead to catastrophic failures. They can lead to formation of cracks, and then therefore stress is going to be concentrated around the regions of the crack, and as we have seen, and therefore it will lead to sudden failures inside the materials, especially if the material is rather brittle. And they have low electrical conductivities compared to non-ferrous alloys such as copper, aluminum, and their densities is very high compared to other type of materials, like non-ferrous alloys such as aluminum, magnesium, or polymers. So they have high densities, which actually limits their applications. Okay, so non-ferrous alloys, they are classified according to the base metal, and there is a distinction is made between cast alloys or wrought alloys. So cast means the alloys cannot, they are so brittle that they cannot be formed or shaped with different manufacturing techniques. But when we say raw alloys, these materials can be deformed with manufacturing techniques. So we are seeing here different types of alloys: copper alloys, aluminum alloys, magnesium alloys, titanium alloys, noble metals, and refractory metals. If we take a look at the copper alloys, pure copper that is very soft and ductile, it has highly resistance to corrosion, and we can also enhance the mechanical and corrosion properties of the copper with alloying, by alloying them. They can be hardened and strengthened by alloying them, but not with heat treatment. So it has a capacity to be strengthened by cold working or solid solution alloying to improve the mechanical properties. The most common copper alloy is brass. Here the zinc is an impurity added to the copper. Some common uses for brass, like jewelry, corrosion resistant applications, coins, etc. Another type of copper alloy is bronze, with the addition of tin and aluminum, silicon, and nickel. These alloys have good corrosion resistance and good tensile strength properties. And as you can see, it is used in bushing and landing gear. So there is also another type, beryllium copper alloys. They have very high strengths, so excellent electrical and corrosion properties, wear resistance. They are though costly, but they can be used in jet aircraft landing gear, bearings and bushings and springs, and surgical and dental instruments. Aluminum and its alloys. Aluminum has a low density, which is 2.7, and steel is 7.9, so you can compare. They have good electrical and thermal conductivities, good resistance to corrosion, and they have high ductility, so it is very easy to deform them. They are easily formed. You can also think about aluminum foil, right? They are able to produce aluminum, very thin aluminum foil from aluminum by rolling. We're gonna take a look at the manufacturing techniques. So it is due to the FCC structure of aluminum, which provides ductility, but they have low melting point. That's the problem. Therefore, it restricts their usage. But the very good thing about that aluminum, they can be strengthened, and this can be achieved by cold working and alloying. There is also, you can do precipitation hardening, that is achieved by heat treatment. And please also make sure you watch the videos I'm sending you. I will send you in a video about the precipitation hardening of aluminum alloys and how it increases the strength, and therefore they can be used in aircrafts as aircraft parts, because this will give them strength besides the low density. I believe we have not covered precipitation hardening, but it is basically in an alloying system. With heat treatment, you are able to form tiny precipitates of different phases in the structure, which provides strength to the material. And in the video I'm gonna send you guys, you can also watch. They explain what it means and how it was discovered, and that actually led to the use of aluminum alloys in aircraft industry. And then magnesium alloys. These materials have the lowest density, 1.7, lower than aluminum. But the problem with this material is it ignites easily, creates a fire danger. It is being used in aircrafts and missiles. Magnesium and its alloys, they are difficult to form. Most fabrication is by casting and hot working at temperatures between 200 and 350 degrees C. Just like aluminum, they have low melting temperatures. Titanium and its alloys. This is relatively a new engineering material with excellent properties. Especially it can preserve its strength at high temperatures, and it has a low density, 4.7. It has a very high melting point and high elastic modulus. They are strong. They can also be easily forged and machined. So we're gonna see forging is a type of manufacturing technique with application of forces. The material can be shaped. Due to these properties, basically, it is used in space applications. It is also being used as biomaterial because it's unreactive when exposed to the body, and it doesn't release toxic chemicals when it is put into our bodies. So what we call this biocompatible material. It has a good corrosion resistance, and therefore usually when there is a part of body replacement is required, such as hip, knee, they can be used as hip and knee implants. Refractory metals, as the name implies, these metals have very high melting, extremely high melting temperatures. That's why they are called refractory. So tungsten has the highest melting temperature of all metals. Therefore, they are being used in applications where high temperature stability, high temperature strengths are required. That's why they are being used in these applications. So noble metals are expensive but soft, ductile, oxidation resistance. These are silver, gold, and they can be used in dental applications. They can be used as in electrical applications because silver is a very high conductivity. And they're also being used as antibacterial materials. You know, silver is put in creams where there's a burn wound. We can put on it to prevent any infection, because they can kill bacteria. Like silver and gold, they damage the bacteria wall. So let's take a look at now manufacturing operations of metals. So several techniques. Here we are seeing one of the forming operation is called forging. Forging is like hammering, and by hammering we are trying to shape the part. And we can also do casting, basically melt the metal first and pour it into a mold cavity, and this mold cavity will have the shape we desire. These processes can be done at cold temperatures, meaning at room temperatures. We call it cold working. They can be also called hot working, meaning if you work at temperatures near the recrystallization temperature of the material, higher temperatures. So there are advantages to disadvantages to both. So cold working, remember, strengthens the material but reduces ductility. This is where the deformation happens below the recrystallization temperature. Remember the annealing process. And in this case, material gets stronger. We call it strain hardening. But you can only do small deformations. You cannot just, for example, let's see, you are trying to reduce the thickness, right? You cannot reduce the thickness to a large extent when you do cold working, because the material is not very ductile. Think about if you heat the material actually above its recrystallization temperature, you are providing ductility to the material. It is much easier to achieve large deformations without actually the material being broken. Okay, so hot working has the disadvantage of oxide formation on the material, because oxidation, remember, is a diffusion controlled process, atomic diffusion. So when you go to higher temperatures, atomic motion rates are increasing, therefore oxidation is increasing. And oxide layers are ceramics, basically very hard and brittle particles which can stuck in the structure after deformation and also provide formation of defects. These points can act as formation of defects, can also decrease the surface quality of the part, which might require further processing techniques to enhance the surface quality. Okay, so fabrication techniques, the book divides it to 3 categories. One is forming. Forming includes forging, like hammering and drawing, and rolling and extrusion, we're gonna see, and there is casting, and some other miscellaneous techniques such as welding, powder metallurgy. So what is forging? Forging is basically like hammering. You see we have a die and we have a blank, the starting material, starting workpiece. After the application of pressures into the die, the workpiece takes the shape of the die cavity, as you can see. This is achieved often at high temperatures because we need some ductility, flow characteristics to the part so it can flow and take the shape of the die cavity with the application of the force. Drawing is usually when you want to produce rods, wire, tubing. In between the die, you see you are pulling the workpiece with the application of tensile force. There is a reduction in the cross-sectional area when the workpiece passes through the die cavity. And you see it initially cross-section was A0, it decreases to A D. And then there is rolling. In this case we have rolls. In between the rolls we also achieve the same thing. The material flows through it and it achieves a reduction in the cross-sectional area. I-beams, rails, sheet and plate, they are all can be formed with this technique. It can be hot or cold rolling. And there is also extrusion. In this case there is a force applied to what we call the billet or the workpiece. Again, cross-sectional area is reduced. This time we are forcing the material to flow through a die cavity. Usually ductile materials are produced with this technique, such as copper and aluminum. And make sure you watch the videos I'm sending you for all these different type of manufacturing techniques. Of course, this is not a manufacturing class, so I'm not going into details of these, but to get a general idea of the things I mentioned here and to get a visual idea what these techniques are, please watch the videos I'm sending you. Casting is a process where we have the molten metal that is poured into a mold cavity of the desired shape, and upon the solidification the metal assumes the shape of the mold, but of course it experiences some shrinkage, so you need to account for those type of processing parameters. Casting technique is employed when the finished shape is very large and complex and no other method that may be practical. So if a particular alloy has a low ductility, then it cannot be formed easily by forming techniques. Then you can do casting. Casting is also the most economical shaping technique. There are several different type of casting techniques are available. One of them is sand casting. That is the most common technique available. So here, of course, as the name implies, as a mold material, sand is used. First, you need to create the mold from sand. Therefore, you need to have a pattern. Pattern will have your part's desired shape. And you pack the sand around the pattern, and then it will generate the mold, right? And then use that mold to do the casting. There is also investment casting. This is also called lost wax casting. In this case, you make the pattern from wax or a plastic which has a low melting temperature. So around the pattern there is a fluid slurry is poured, and that sets up to form the mold. After you form the mold, you basically heat the material, the complex with the wax and the slurry together here. You melt it, the pattern melts, it's burned out. It will leave the mold cavity with the desired shape right here you are seeing. And then you pour your metal that you want to cast right here, right? And wait for it to solidify. So basically the lost wax comes from the fact the pattern is made out of wax and you are melting it away. There is also die casting. In this die casting, the liquid metal is forced into a mold under pressure at a relatively high velocity and allowed to cool. The difference here is the die is permanent. In the steel, in the sand die casting, right there, sand casting. What you were doing is once you cast the part, the metal solidified, and you removed your part, you actually destroy the sand, the mold. So each time you are doing casting, you again need to form the mold again and again. So in this case, on the other hand, in die casting, you have a permanent mold. That's why it is made out of strong materials like steel. And steel is forming your die, which has the mold cavity. And basically the mold opens up and then releases your part after the casting is done. This technique provides rapid casting rates because you can use the die again and again. You don't have to form it again like you do in sand casting. And this will of course reduce the costs. And there is also, this one is also for alloys that have low melting temperatures. And because the die is made of steel, you don't want to go to very high temperatures that might cause damages to the die material. And there is also continuous casting. After we have the molten metal from the furnace, we can cast it into large ingots, like simple shapes like this. And these ingots are then being used in further operations such as rolling or extruding, etc. This is of course limited to simple shapes. Some miscellaneous techniques, one of them is powder metallurgy. In this case, as the name implies, this is suitable for high melting point metals and ceramics usually, but we are talking here for metals. So here what happens is you have the powder form of the metal, and then you apply pressure and heat. What happens, those particles of metals diffuse into each other, and atoms diffuse into each other and basically fuse the particles into each other, as you can see. Of course, with high temperatures, this is diffusion controlled. Atoms diffuse into each other, basically attaching the particles into each other, gluing the particles into each other. And this will lower the density, of course. I'm sorry, it will increase the density, right? More compact. Okay, so there is another technique here. Welding, and you guys are familiar with this, I'm sure. This is when if it's a large part, then fabrication of the whole part at once might be difficult. Therefore, you produce two different pieces and then weld them to each other. During the welding, a filler metal is used to connect to different pieces. So as you can see, a certain region of the weld will be affected because you are going to high temperatures to be able to weld two pieces together. And the thing about welding is there is this heat affected zone where the microstructure of the materials are actually has been changed. Okay, so we have seen what annealing is, right? It is a heat treatment. The material is exposed to an elevated temperature for a long period of time and then slowly cooled. So there are reasons why we do annealing, which is one is to relieve the stresses, and then increase ductility, reduce the strength, and produced a specific microstructure. So there are different types of annealing techniques. One is process annealing. Process annealing is done to eliminate the effects of cold working, basically to softening or increasing the ductility of previously strain hardened material. Another one is stress relief. In this case, there can be residual stresses that may develop inside a workpiece. Then we want to relieve those stresses. How come internal stresses can develop? For example, you are doing machining and grinding. This can induce stresses to the material, and this will make material susceptible to stress, corrosion, cracking, etc. And there can be non-uniform cooling. So if throughout the piece you have different regions that are cooled differently, they will have different ductility. And you want to do homogenization, you want to homogenize, right? You want to relieve the stresses throughout the piece that is forming. And also there can be phase transformation that are inducing stresses to the structure. And we want to remove these because if there are stresses like tension, compression in certain regions of your part, when you actually cut a piece of it, there can be a warping or distortion of the piece. And this can be eliminated if we do stress relief annealing heat treatment. Basically, we heat up the piece of metal to a temperature and then held it long enough to attain a uniform temperature, then cool it back to room temperature in air. Another one is full annealing. Full annealing is a term applies to low and medium carbon steels that will be machined and or will be experiencing extensive plastic deformation during forming operation. What happens here, the alloy is heated to a temperature about 50 degrees above its austenite line, and then depending on, of course, what composition range you have, you might end up with an austenite or austenite and cementite phase, and then you cool it in the furnace by just turning it off to the cool room temperature, which will take long time, right? Several hours to cool. Such a material will have a coarse pearlite structure that is soft and ductile. And there is ferrodizing. This is for medium and high carbon steels, which might still be too hard to machine and deform plastically. And these materials can be heat treated to develop spheroidized structure like we have seen previously. And spheroidized steels will have very good softness and ductility. And they can be easily machined and deformed. And in the spheroidizing treatment, basically cementite particles form spheroid particles. And this can be achieved by heating the alloy just below the eutectoid temperature and then holding it at that temperature for up to 25 hours. And there is also normalizing. In normalizing, let's say you have irregularly shaped large grains that are varying in size throughout the part. This is, for example, if you do a rolling in a material that can result this type of grain sizes and their variations in the structure. Therefore, a normalizing treatment is done to refine the grains, basically decrease the grain size and produce a uniform and with a desirable size distribution. We are seeing the continuous cooling transformation curves here and the cooling curves. As you can see, the red one is quenching. Remember, when we do quenching, when we start a temperature above eutectoid and we quench it immediately, austenite goes to martensite, as you can see here. Okay, and then it is like full martensite at room temperature, and if you keep it at room temperature, it is now martensite. And what you can do is you can do tempering and transform some of those. Tempering means go to remember what tempered martensite is. So you heat up the material to higher temperatures. In this case, like about somewhere between 300 and 200 and 300. There you keep it for some time, and then when you cool it back to room temperature, so we heat it up, keep it, and then cool it back to room temperature, and then keep it at that temperature. We are seeing some of those martensite might turn into bainite, some cementite together with alpha ferrite. So there is also full annealing, like shown with the blue. In the full annealing, remember, we cool it down in the furnace, so it takes longer time to cool it down, and then you are able to form the perlite structure. Because we are going from austenite region to perlite region, and remember, once the perlite forms, even you go back to the room temperature here, right, it is still perlite. Once the perlite forms, it doesn't go back to bainite. Okay, you either go from austenite to bainite, austenite to perlite, or austenite to martensite. Okay. So hardenability is the measure of the ability of the material to form martensite, to be able to be hardened. So this is done with Jomini and quench test. So in this test, you have a specimen which is in the austenite phase. If you watch the videos, you're gonna see first you put your specimen in the furnace. Make sure you have austenite phase, and the end of the specimen is cooled rapidly. As you see, there is water at the tip of your specimen and trying to cool it down, right? We are doing quenching actually. So the quench end is cooled most rapidly and exhibits the maximum hardness. 100% martensite is the product at this position for most steels, but the cooling rate decreases with the distance from the quench end, right? And there is more time for carbon to diffuse. Softer perlite structure is observed away from that tip that is being quenched, and which there might be some mixtures of martensite and bainite. And after that, hardness test is done to measure the hardness starting from that region and along the length of the part, which will give idea about the hardenability of the material. And you can see then you plot this hardness as a function of the distance from the quench end, and this is how it's decreasing, right? Initially at the quench end the hardness is very high, and then it's decreasing as we move away from the quenched end. We can say then it's still is highly hardenable if it retains large hardness values for relatively long distances. But if it doesn't have a good hardenability, if it has a low hardenability, then it will not retain this hardness when we keep moving away from the quenched end. And this is the information we obtained by measuring the hardness throughout the length. And of course you guys expect the quench end will have the highest cooling rate because it is in contact with the water. But as we move away from the quench end, the cooling rate decreases. And with the cooling rate decreasing with the distance, then the material will have different type of cooling curves, therefore different type of structures throughout the length. The initial part, which is the dark blue, right, will form due to fast cooling rates, will form martensite. But then from austenite we're gonna form martensite and pearlite as we go to lower cooling rates and move away from the quenched end. And then it will be fine pearlite and then pearlite as we go to very smaller, slower cooling rates. So pearlite, little bit fast cooling, fine pearlite, and more faster cooling martensite and pearlite. And if you have a very quick cooling at the quenched end, you have martensite. So in the first figure we are seeing hardenability curves for 5 different alloys, each with the same amount of carbon. So 4340 alloy, which was the alloy of nickel, chromium, and molybdenum. These ferrous metals can preserve their hardness value as we move away from the quenched end. On the other hand, the plain carbon steel with the 0.4% carbon, as you see 1040, that is when we go away from the quenched end, it quickly decreases hardness values. So it doesn't have a good hardenability. This one has a good hardenability, this one doesn't. So the reason for this in alloy steels you have a good hardenability is actually the alloying elements you contain, like nickel, chromium, molybdenum. These are, remember, when we add the alloying element, it creates changes in the TTT curves. And in this case you can see the nose is shifting, nose being this part, right, is shifting from A to B, which means you can easily form martensite even if your cooling rates are not very fast, as you can see, because normally you need to cool this quickly when you are at the position A, but now since A moved to B, then you can cool a little bit slower but still have martensite in the structure. Therefore slower cooling rates will even result in martensite. Therefore, for these alloy steels, one of them is 4340 here, you can preserve the hardness as you move away from the quenched end. There are other factors that are affecting the quenching. One of them is the quenching medium. So normally you might think we do quenching in water. Actually, there are a lot of other different liquids where you do the quenching. And the quenching medium can have different thermal conductivities. That's why it can affect the heat removal from your sample. How quickly it removes the heat will of course changes the structure, mechanical structure, and therefore people came up with a variety of quenching medium which can create different type of structures in the material. And here we are comparing three. Actually there are more, but we are comparing three. You can cool in the air, you can quench it in the oil, or you can quench it in the water. So severity of the quenching is the highest when it comes to water. Therefore, the highest hardness values are achieved with the water, and air is the lowest in both situations. Of course, the severity of quenching, what is happening? Okay, severity of quenching, I meant it's the rate of cooling. So the more rapid the quenching is, it's more severe. The degree of agitation of the medium is also effective in the heat removal. So don't forget to watch the videos. Here I also showed you a video of an oil quenching and tank agitation when they do the quenching. So when you consider the specimen shape, remember the heat is dissipated from the surface to the quenching medium. So the rate of cooling will depend on the amount of surface area compared to the volume. So because that's where the heat is dissipating, right? So basically if this ratio is larger, basically the surface area to volume ratio, if this is larger, then you expect more rapid cooling rate. Therefore deeper the hardening effect. Basically it's more strengthening. Think about if you have irregular shapes with edges and corners, they will have very large surface to volume ratios. Therefore, they are more easier to harden by quenching. So if you think about it, like the center regions will have low area to volume ratios, therefore it will have a low cooling rate and low hardness compared to surface, where the surface exposed to the quenching medium is gonna be having high surface area to volume ratio. That will of course result in high cooling rate and therefore high hardness values. Okay, precipitation hardening is one of the techniques that we use to basically increase the strength of the materials. You can add this to technique to besides the things we have learned in the strengthening of materials, such as solid solution hardening, cold working, work hardening, strain hardening, meaning all those you can add this one also. Precipitation or H hardening. These are the same terms, okay? H hardening or precipitation hardening. This is usually in aluminum alloy systems, and you can watch the video about that also. I sent you guys. So how do we do precipitation hardening? You are not adding additional particles to the system. What you are doing is using alloy system itself and using a certain type of heat treatment by looking at the phase diagram of the alloy. You are creating little particulates. So how do we do it? First, you see, if you look at aluminum copper alloy system, alloy system, you are seeing that you initially start at point A. At point A, you just have alpha solid solution of aluminum and copper. And this solid solution is quenched to room temperature very quickly, which is you coming into point B. Okay, when you do that, you don't provide enough time for theta particles to form, because at point P you are supposed to have alpha and theta together. But if you quench it so quickly, you don't let theta to form in the structure. But then, what if you either provide time to the material. So you keep it at room temperature for a long period of time, or you can also heat it up to a temperature at point C, where you might start to see the nucleation of theta particles. You can also do that. And these theta particles will be in nanosizes, very tiny, that are nucleating from the alpha phase. And this will create obstacles for the dislocations again, therefore strengthening the materials. Other alloys that can be the precipitation hardened is copper, beryllium, copper tin, magnesium, aluminum alloys. Not all alloys can be hardened with precipitation hardening, but some alloys can be done with strength can be increased with this technique. The reason it's also called age hardening, it's because with time you are strengthening the material. So you see, first we are at a point keeping the material at point A, and we heat it up to a certain temperature, then we quench it to the point B, then we increase the temperature and kept the material at point C at that temperature, you see, for some amount of time, and then we go back to room temperature, and then material is kept at that temperature, and now it has increased strength. Now we are seeing how precipitation hardening affects the tensile strength and ductility. So we have a certain aluminum alloy, and we are seeing how the tensile strength is changing with time. We start with the non-equilibrium solid solution, meaning you are at point B. Okay, you are at point B. With time, the tensile strength is increasing. Okay, but there must be an optimum time where the maximum strength is achieved, because if you keep holding that part at that temperature for more than necessary, then those small precipitates will become large precipitates, because they will start to coalesce, they will start to get together. And you don't want them to get together, because whenever they are very tiny sizes, like nano sizes, they provide the best strengthening, best obstacles to the dislocations. When they grow larger, their effect is diminished. Therefore, actually, precipitation hardening is not a good technique to strengthen the material if you're going to use it at high temperatures. Because if you have strengthened the material with precipitation hardening, and if you use that material at high temperatures, it's going to lose its strength. And that's also showing you that the heat treatment temperature is an important effect in the amount of tensile strength that you can achieve, optimum strength that you can achieve. And of course, it affects the time. If you go to lower temperatures to heat treat the material and keep it aged, then of course it will take more time, maybe up to a year. All right, so there is a certain amount of time and at that temperature that will give you the maximum strength. Okay, so it of course the same way, the ductility trend, but opposite, right? So when the tensile strength is maximum, you achieve the lowest ductility in both samples. So what we have learned is we have learned ferrous alloys, steels, and cast irons. Make sure you understand the difference between them, and make sure you can actually identify from the micrographs what type of cast and steel and cast irons we have, what are the properties of them. And non-ferrous alloys like copper, aluminum, titanium, magnesium alloys, what are their specific properties. We looked at different fabrication techniques briefly. We looked at them like forming, casting. We understood what hardenability means. It's not related to hardness. Hardenability means what can be the degree of hardness we can achieve along the length of the material if we expose one end to rapid cooling rates like quenching. So it is the measure of ability of a steel to be heat treated and strengthened with the increasing hardness, and this increases with the alloy content we have seen. And then we learned about precipitation hardening. Precipitation hardening was due to precipitate particles forming in the matrix phase that are preventing the dislocation motions, and some alloys were able to be strengthened with this technique, such as aluminum and magnesium alloys. That's it.